So by now you guys are familiar with Newton's first two laws of motion. Newton's first law and Newton's second law. Newton's first law said that an object at rest stays at rest and an object in motion stays in motion unless acted on by a net force. Newton's second law was really just an equation, right? Sigma F equals ma, one of the most powerful equations in physics. Newton's third law is probably the one that you're most likely to have heard before, although maybe not in the context of physics. Newton's third law says that for every action, there's an equal and opposite reaction. Now, in the context of physics, what we mean by action is a force, and what we mean by reaction is another force. So what this law is saying for us is that for every force that exists anywhere in the universe, there is an equal and opposite force somewhere else in the universe. What does equal and opposite mean? Well, equal just means those two forces have the same magnitude. And opposite means that they are moving in different directions. So equal and opposite mean equal magnitude, but opposite direction. In a sense, what I like to think of here is that every force has a buddy. If there's a force somewhere in the universe pulling left, then we know somewhere else in the universe there's going to be a force that's pulling right with the exact same magnitude. Now, to demystify this a bit, I'm going to give you a few examples. And I talk about pairs of forces existing in the universe, but often they exist very, very close to each other. So here are a few common situations where Newton's third law really applies well. First is a runner accelerating. Well, when we think about how this happens, we say, well, if I wanted to go running and I wanted to speed up, I would use my feet to push the ground, and I'd push the ground sort of backwards. I'd push against the ground, behind where I want to go. Now, because forces have to obey Newton's laws, and Newton's third law says there must be a equal and opposite force to this, turns out that force is coming from the ground pushing on your foot. So when you push the ground backwards, because of Newton's third law, the ground pushes you forward. And that's what actually makes you go forwards. If you think about it, it's kind of weird that if you want to go forward, you push the ground backwards. Wouldn't that just make the ground go backwards? Well, we can get into that, but it actually does a tiny, tiny bit. But because of Newton's third law, if you push the ground backwards, it's going to push you forwards, and that's why you start to speed up. Another example of Newton's third law in action is rockets. And this is a classic example. And a lot of times people really do not fully understand how rockets work. They think a rocket's something like a jet engine or a propeller, and it pushes against the air that's around it. But there's something fundamentally a bit different going on here. So the way a rocket works is the rocket pushes its exhaust down. What I mean by exhaust is inside the rocket, there's a combustion reaction going on, and there's all sorts of sort of smoke and gases being created. And the rocket takes those gases and it pushes them out of its bottom and pushes them downwards. Now, because of Newton's third law, if the rocket pushes the exhaust down, the exhaust must push the rocket up. So here's what that looks like, in real time. I think this is a SpaceX rocket. And it is inside here creating a lot of exhaust gases as it burns its fuel. And it takes those gases and it shoots them out the back. We can see all this smoke coming out the back. And the harder the rocket pushes these gases down, the harder the gases are pushing the rocket up. And that's actually where the rocket gets its thrust from. The next example I'll talk about is a bug hitting a windshield. Now, we're all probably pretty familiar with that. If you drive into a bug, your car is going to push the bug forward pretty hard. That's what causes the bug to often be obliterated into many, many pieces on your windshield. So here we see a bug that's clearly been hit by a windshield. And you can imagine that when this happened, this bug felt a pretty big force in that direction, towards the right. And that force was strong enough that it broke a bunch of the bug's tissues and caused this little mess we see here. But what you don't necessarily think about as much is that when that collision happened, not only did the car push the bug to the right, but the bug actually pushed the car to the left. And what Newton's third law even tells us is that those two forces are equal. So yeah, the car pushed the bug pretty hard to the right, causing the bug to burst. But the bug pushed the car equally hard, equal and opposite, remember, to the left. So how come the car didn't burst into many, many pieces like the bug did? Well, the car is built a bit stronger. The car is heavier. So that's why we have the bug bursting, but not the car. But realize that both of them felt the exact same force at that moment of impact, but in opposite directions. That's what we mean by equal and opposite. So the car pushes the bug forward. Therefore, by Newton's third law, the bug pushes the car backward. Now that we know all of Newton's laws, we're going to start to apply them together bit by bit. And one of the key tools we need when we want to apply Newton's laws and analyze problems to do with forces is we need to know how to make a free body diagram. In essence, this is a diagram of all the forces that are acting on an object. We actually did some free body diagrams in the previous lessons. If you'll recall, we drew a diagram of a book with all the forces acting on it as it was sitting on a table and as it was falling off the table. But we didn't call those free body diagrams at the time. So we're going to get into some of the specifics I want you to keep in mind when you're drawing these diagrams. As I like to say, there are two rules for drawing FBDs, or free body diagrams. The first rule in a free body diagram is that the body must be free. Makes sense. What does that mean? Well, it means we're only drawing the object of interest. We're not drawing other stuff around it or attached to it. It's free, sitting there by itself. So if I wanted you to draw a free body diagram for a person who happened to be sitting on a chair, you would draw the person, but you wouldn't draw the chair that they're sitting on. You wouldn't draw the ground that their feet are resting on. You wouldn't draw the wall behind them. You're just drawing the body of interest, not the other things that it might be touching. So once you've got that part down, the next thing you're going to do in a free body diagram is you're going to draw all the forces that are acting on the body. Now, as we move forward in this unit, we're going to learn about a number of different types of forces. And we're going to be drawing these forces on free body diagrams all the time. And I want to just, before we dive into any of these forces in great detail, I want to give you a quick overview of some of the most common suspects that we're gonna run into. So the first force that we're going to run into all the time when we draw free body diagrams is gravity. And instead of having you write out the word gravity on your diagram all the time, we're going to use a symbol for it. And the symbol we're going to use for gravity is Fg, which stands for the force of gravity. Now, like I said, we'll go into detail on how all these forces work later. For now, I'm just going to give you a quick synopsis. And what I want you to know about the force of gravity is it's a pull, as opposed to a push, that comes from the Earth. Right? We all feel the force of gravity pulling us down, pulling us towards the Earth. It's why when we jump, we don't float up into space. Now, a finer point about this is gravity doesn't just pull things towards Earth. Gravity will actually pull you towards anything that has mass. So the moon has mass. If you're on the moon, gravity will pull you towards that. Mars has mass. If you're on Mars, gravity will pull you towards that. Even weird things like the screen in front of you that you're watching this video on, that screen has mass. And there's a tiny, tiny bit of gravity that's pulling you towards that screen. I don't want to get into this too much for now. We'll elaborate on that more later. Another force that's going to come up all the time is the force of friction. And the symbol we're going to use for that, again, so we don't have to write friction out all the time, is FF, for force of friction. Now, key thing I want you to know about friction is this. It always opposes motion when an object slides or tries to slide, and it acts parallel to the interface between the two objects. Now, let me illustrate what I mean by this. Here's an example of friction at work. These two guys are trying to push this couch. So the first thing I said about friction is that it always opposes motion. These guys are trying to move the couch to the left, so friction opposes that. Friction pushes the couch towards the right. So it's really fighting motion. Friction tries to slow down or prevent motion. If these guys hopped on the other side of the couch and started pushing it to the right, friction would then switch around and push the couch to the left. Now it does this either when the object is sliding or when it's trying to slide. So we can't really tell from this picture whether these guys are actually moving the couch. It's possible this couch is in motion, to the left, going across your screen, in which case friction would be moving it or would be pushing it to the right, trying to slow that motion down, trying to stop it. And that's why if they stopped pushing, the couch would really quickly come to a stop because friction slows it down. But even if the object isn't actually sliding, even if it's just trying to slide, and this looks like what is probably happening in this photo. These guys are trying to get the couch moving, but they're not really having much success. That's because friction is pushing against them. So whether the couch is actually moving or whether it's just trying to move, friction is going to oppose that motion or that attempted motion. Now, the other thing I said about friction is that it acts parallel to the interface between the two objects. Now, the two objects I'm talking about here are the couch and the place where friction is existing, which is on the floor here. Right? Friction happens right here between the couch and the floor. And if you can imagine that there was some paint on the bottom of this couch's leg here, that paint would leave a sort of a circular mark on the floor. And that circular mark is what we refer to as the interface between the couch and the floor, the area where the two are touching, are in contact. And friction can act parallel to that interface, to that area. So that area is kind of flat, horizontal on the floor. Friction can act to the right if the couch was going to the left. Friction could act to the left if the couch was going to the right. Friction could kind of act towards us if the couch was moving away from us, etc., etc. But it has to be parallel to that interface. What friction couldn't do is push the couch up, as up would not be parallel to that paint mark that's on the floor, that contact area. So friction always opposes motion when an object slides or tries to slide, and it acts parallel to the interface between the two objects. The next force that I'm going to talk about is called the normal force. And that has the symbol Fn for force normal. Now, force normal occurs whenever an object slides or rests against another, and it acts perpendicular to the interface between the two objects. So there's some similarities and some differences with friction here. And I'm going to pull us back to that same image we were just looking at. So again, whether these guys are actually moving the couch or they're just trying to move the couch, there's going to be a normal force. Now, what the normal force does here is it actually comes from the floor and it holds the couch up. So there's gravity pulling this couch down, but there's also the normal force or the force of the floor supporting the couch. A few days ago, we would have just called it the gravity force down, and we would have called it the force of the floor up. But now we're being a bit more sophisticated. Instead of calling it force from the floor, we're calling it the normal force. So whether these guys are successfully moving the couch or just trying to move it, that normal force is there. It's holding the couch up. It's stopping the couch from falling down through the floor. Unlike friction, that normal force has to be perpendicular to this interface, perpendicular to this little paint mark. So in this case, the only really real option for the normal force is straight up, right? Perpendicular to the floor. Friction can be in kind of any direction parallel to the floor. Normal force has to be perpendicular to the floor. The next force I want to talk briefly about is tension. We're going to give that the symbol Ft, so we don't have to write tension out all the time for force of tension. Or sometimes we'll actually just give this force the symbol capital T. You'll see I might use both of these. Things to know about tension. It's the force that exists at both ends of a rope and within it. So here's an example of a rope that's being used to pull something, as ropes often. Now what this says is the tension is the force within the rope. So you can imagine this rope looks like it's pretty tight. It's pretty taut. It's not going to be sort of loose and dangly. And that's because this rope has tension. And the tighter it is, the more tension there is within the rope. So that's what I mean by tension being the force within a rope. Now it's also the force at this end of the rope and the force at this end of the rope. So over here, this rope is getting pulled in that direction by the car. And over here, the rope is probably getting pulled in the opposite direction. Now, what's important to realize here, and this isn't always intuitive, is that the force with which the rope is getting pulled this way, and the force over here that's pulling the rope that way, and this tightness within the rope are all the exact same. If one of those becomes bigger, all of them become bigger. And this is a little counterintuitive, especially in certain situations. We'll talk about it more later. But for now, you need to know that this word tension, or Ft, we use to refer to how tight a rope is and also the force that's exerted by the rope at both of its ends. I say here this assumes that the rope is massless, which seems a little bit ridiculous for a rope. More on that later, but for now, I kind of liken this to how in kinematics we often assume that there was no air resistance. In reality, there's always air resistance, but it's so small we can ignore it. Same here with ropes. In reality, ropes always have mass, but generally that mass is so small compared to the other things in the problem, like this car over here, that we can ignore it. So referring to a massless rope is actually a pretty common practice in physics. All right, the last force I'm going to talk about is called the elastic force or the spring force. And that has the symbol Fe or Fs, or force elastic or force spring. And the thing to know about this is it's the force from something being stretched or compressed. Often we think of elastic bands or springs. So imagine this spring here. If you were to put your hand on either end of it and squish it, make it smaller, it would push back on you. And that's called the elastic force. That's force you're feeling from the spring pushing back on you. That's an example of the elastic force or the spring force. Conversely, if you grab both ends of the spring and you tried to pull them apart and make that spring longer, you'd feel the spring pulling against you, pulling your hands together. That would also be the elastic force or the spring force. So this is the force from something that's being stretched or compressed. Okay, now let's tackle a problem. Draw a free body diagram for a sled being pulled at constant velocity. So remember, our first rule of free body diagrams is that the body must be free, meaning I draw the thing I'm interested in, my sled here, but I don't draw anything else. I'm not drawing the ground that it's sliding on. I'm not drawing a rope that's attached to it. I'm not drawing the reindeer who are pulling it. The body must be free. I draw only the object I'm interested in, not the things around it or the things it's touching. The second rule of free body diagrams is we draw all the forces acting on the object. So right off the bat, I'm going to have a normal force. This sled is probably resting on some snow on the ground, and that ground is supporting it. It's holding the sled up, stopping the sled from falling. And you can see here we're using the symbol we came up with for the normal force, Fn. Similarly, the sled is experiencing a gravitational force, pulling it down. And again, here I'm using the symbol we use for gravity, Fg. So that's good so far. We also said this sled was being pulled. So over here, I've probably got, I don't know exactly how this is happening, but in some way or another, there's a force pulling the sled to the side. Now, I think that most often when sleds are pulled, it's because they've got a rope or something tied to them, which means that probably the best name for this force that's pulling the sled to the right because it's coming from a rope is Ft, or tension. But you could also imagine that maybe there's a person over here who literally just stuck their hand on the sled and is dragging it behind them, in which case maybe I'd call this F person for the force from the person. Or sometimes we use the term F app for an applied force, when an object directly contacts this and applies a force to it directly. Now at this point, you might think we're done. We've got gravity pulling down. We've got the normal force from the ground supporting the sled, stopping it from falling. And we've got tension over here, pulling the sled to the right. But a key thing in this problem is that this sled has constant velocity. And I'll remind you, Newton's first law tells us whenever something has constant velocity, that means its motion isn't changing, the forces must be balanced. And if we look at our free body diagram so far, doesn't look like these forces are balanced. Right? These two, Fn and Fg, seem balanced, but there's nothing balancing out Ft. If this sled is at constant velocity, there has to be something balancing out Ft. And that thing is going to be friction. Right? No matter how nicely waxed these sled runners are, there's going to be a bit of friction between it and the snow, and that's drawn over here. So now we can see Fn and Fg have equal magnitude. They're in opposite directions, though they cancel out, and Ff and Ft cancel out. So I have all the forces are balanced. There's no net force, and thus I would expect that this sled would have constant velocity. So there you go, your very first free body diagram.